In this video, we will be reviewing some basic logarithmic properties and using them to set up and solve logarithmic equations. Let's get started. We begin by reminding ourselves how we could take two logarithms with the same base and condense them into a single logarithm. Remember that if the same base logarithms were added together, we would condense their arguments by multiplying. Very nice. So we would have log base b of m plus log base b of n rewritten in condensed form as log base b, and the argument would be m times n. On the other hand, if we were subtracting two logarithms with the same base, their condensed version would be log base b of m over n, where order matters. So the first logarithm, which was positive, would have its argument on top. Finally, there was one other important log property I wanted to remind you of before we get started today. And that is, if we have a logarithm of an argument being raised to a power, what can we do with that power? That's right, we can bring it down in front of the logarithm. In other words, this r power would come in front and we would have r times the log base b of argument m. Why would we care to do that? Well, in the next video, we'll be talking about exponential equations, and the only way that we can solve an exponential equation is sometimes to bring that power in front. And to do that, we'll need logarithms. Remember, exponentials and logarithms are inverse functions. They undo each other, allowing you to solve one type of an equation with the other. So let's continue with an example below. I also have listed in your notes there a link to some more properties if you think that you need to refresh yourself with logarithms. So we remind ourselves here in the box below of how we switched back and forth between logarithmic and exponential form. Remembering that the base, which is your subscript below, is being raised to the power on the other side of the equal sign. So this would say, for example, base b to the power of y should end up giving me my argument x. In other words, we think b to the y is equal to x. Well, let's apply that now to our example below. It says log base 3 of x equals 2. How could I rewrite that in exponential form? See if you can do it yourself. That's right. 3 to the second power is equal to x. If that's what you had, great job. Now we know that means that x is 9. And in this case, because 9 is a number greater than 0, so x equals 9 in that case, this would be an acceptable answer because whenever we are solving for a logarithmic equation like the one we just did, we have to make sure that every argument has inputs which are allowed, which are legal. And since 9 is in fact greater than 0, that is a satisfactory input. So this is a satisfactory answer that is possible. All right, let's continue using these logarithmic properties to condense and to solve equations. Example 1 says, can we simplify the logarithmic expression by hand? Here we have log base 2 of 160 minus log base 2 of 5. See if you can remember which property would apply here to condense this logarithm. That's right. We're going to condense by combining the arguments using division. Very good. So this would become log base 2 of 160 over 5. Now, while that's true, you have condensed it into a single logarithm. There's more simplifying that you could do, and we always expect our students to simplify as far as possible to make it easy for the reader. We know that 160 divided by 5 is really, that's right, 32. And this is actually a logarithm which we could simplify by hand without even using technology, because hopefully we can see that 32 is really 2 to some power. This is 2 to the 5th. Very good. Now, if you remember what a logarithm is, this is saying 2 to some power is equal to this argument. Well, 2 to what power would equal 2 to the 5th power? Well, that would have to be 5, wouldn't it? So this actually is just 5, but a shortcut, let me grab another color here for our shortcut here, would have just been to remember that if you know a logarithm base b has an argument, but that argument is actually the same as your base, and it's being raised to some power, then the answer is just that power, because b to the m will give you b to the m. That kind of should make sense, I hope. Okay? So this is another fun property that you're always going to want to have ready to roll if you need it. Okay, Let's head over to another example and see how good we are with our log properties. Example 2. Could we expand the logarithmic expression below? Now notice the difference. Last time it asked me to rewrite the logarithm or the series of logarithms into a single condensed log, which is very helpful for solving logarithmic equations that we'll be doing later today. But suppose you were in calculus, okay? One day hopefully you make it to calculus, all right? And you were asked to take something called the integral of this nasty logarithm. You would not want to begin to take the integral of this big logarithm that's very complicated. Instead, what you would want to do is to remember that you can expand this logarithm into separate little tiny logarithms, which are much easier to handle in calculus in that context. So let's go ahead and practice our expanding skills. It's basically the opposite procedure of condensing. Now we're expanding. So let's take a look at that. Well, here's what I notice. I currently have a logarithm base 4, and inside the argument, I have a quotient. I have division. So if we go back to our notes, or if we think back to our properties, this would be the situation where we could split the logarithm into log base 4 of something, and then what would be my symbol in between my two log base 4s? Can you think about what that would be? Feel free to pause at any time and do it yourself and then check. Yeah, it would be subtraction, wouldn't it? So because it was a quotient, we're going to use subtraction here. Okay, so let's take a look at what our two arguments should be. The top argument was x squared minus 9, so that will go first for our first logarithm. And the bottom one was the trinomial, but hopefully you can see that factors. What factors of it are there? Factors of 8 that add up to -6. That's right, -4 and -2. So x minus 4 times x minus 2 is another way of writing that argument. And you might have already noticed, I'll just go ahead and erase it here now, that x squared minus 9 can also be factored. It's a difference of squares. So rewriting that argument becomes what now? That's right, x plus 3 and x minus 3. So once we've rewritten each argument as a product of factors, the key word being product, right? We can continue the the expanding process, but carefully. Remembering that if we aren't truly expanding here, we know that if it was multiplication in the argument, unlike division, which ended up expanding out into subtraction of logs, multiplication ends up expanding into addition of logarithms. So we should have log base 4 of something, in this case our first argument, x plus 3, let's say, plus log base 4 of our second argument that was being multiplied there, x minus 3. Now that's the first two logarithms after expanding that product inside. But be very careful what happens after that. Notice we had this minus sign. We need to be careful to remember that a minus sign affects everything after it. So it will affect the entire entity that we are about to expand. So let's do that carefully. As we expand this product again, we'll get two logarithms with base 4. We must remember our base. So log base 4, let's say, of x minus 4, plus log base 4 of x minus 2. But we still haven't completely finished expanding. Why is that? That's right, because we could distribute that negative sign to each term. So our final answer should be logarithm, whose base is 4, of the argument x plus 3, plus log base 4, argument x minus 3, minus logarithm base 4 of x minus 4. Here's the clincher, minus logarithm base 4 of x minus 2. Now, if you had done that problem on your own and you were checking your work with me, chances are that sign is where you might have made your mistake. Okay? Lots of us make that mistake if we're not paying enough attention. That's why I really encourage my students to put in parentheses anything that comes after that negative sign, so I can remind myself I have to distribute the negative change to each term following it. All right, now again, why would this be helpful? When would it be helpful? If we were in a calculus problem trying to integrate a complicated logarithm by first expanding it into separate pieces like we've done here, we could then apply our integration techniques to the smaller and easier situations. So this will be an important skill to brush off, to refresh as you get ready for your calculus classes. All right, let's head over to some more complicated ways that we can use our logarithmic properties. Well, we can use them to solve logarithmic equations. But remembering, the first step will always be to condense, if possible, and then begin solving an equation that has logarithms. There's two different situations that should pop up when you're dealing with an equation that is involving logarithms. The first is the easy case. I'll number them for you. The first case is when we have one logarithm equals another logarithm, and they happen to have the same base. Now, if they have different bases, this property will not work. But if they're the same base, the only way that can be true is if their arguments are the same, if their arguments are equal. So that's what I'm doing here. I'm setting my arguments equal. And we're going to do an example of that later on, but an easy example could be log base, let's say 10, so I won't write it. Remember, that's a common log, of x equals log implied base 10 of 2. In that situation, because they're both the same base on each side, a log equals a log with the same base, we just set the argument equal. That would mean that x would have to equal 2. Then we would check our answers. Remember, we always check our answers when we're solving a logarithmic equation. And we make sure that every argument is still greater than 0 when we put that input into the argument. In this case, inserting 2 into the argument here is still greater than 0, so it would work. Let's see what the second type of situation will be. The second type of situation would involve if instead of a logarithm equals another logarithm with the same base, what if we have a log equals some number? Well, that's when we're going to simply switch back to exponential form and then solve from there. So here in this case, we take our base to that power and notice that it has to equal that argument. So b to the r equals x for log base b of x equals r. Well, let's apply one of these two rules to an example, shall we? We have log base 10 implied, because it just says log, of x plus log base 10 of x plus 9 is supposed to equal 1. Now, practically speaking, this could be interpreted as a graph. You could go to desmos.com or to a TI calculator, and you could type the left side and the right side as separate graphs, and you're really saying, when does this logarithmic graph cross the line y equals 1? Does it ever happen, and if so, where? So let's take a look at what this would be. First thing I would notice is that I could condense my logarithms because they have the same base and they're being added together. So after I condense, I would get, try it on your own if you like, log base 10 of x times x plus 9. I'll put it all in parentheses to remind myself that's the entire logarithm, equals 1. Now it's imperative to notice that you recognize what the base is implied to be. In this case, we agreed it's implied to be 10 anytime it's just saying log. So we're going to write that in so we can remind ourselves. And now I can switch back to a exponential form because I have a log equals a number. This is in fact an example of our second type of logarithmic equation where we have a log equals a number. So I'm switching back to exponential. And let's see what happens. 10 to the 1 is just 10. Equals my argument, which I could distribute as x squared plus 9x. At this point, this is technically just a lower level algebra question, right? We're asking you to solve a quadratic equation. But the kicker will be, once you get your two answers for x, check them. Do they truly keep your arguments positive? Otherwise, they're not valid inputs. So let's see what happens. Well, moving 10 to the other side gives me 0 equals x squared plus 9x minus 10. I could use the quadratic formula, I could complete the square, but this one does in fact factor, so that's always easiest if it works. What are the factors of negative 10, so different signs, that add up to positive 9? What would that be in this case? That's right, positive 10 and negative 1. So x plus 10 and x minus 1. But setting each factor equal to 0 by the factor theorem would mean that my two potential answers would be either x is equal to negative 10 or x is equal to positive 1. Before I declare with victory, I found the two answers, the two places where this graph should cross y equals 1. Back up. In fact, if you were to check in Desmos or in your graphing utility, you'd see that that's not true. There's only one place that this graph actually crosses the line y equals 1, and that's the positive answer. And why is it not negative 10? Well, if you were to go back into your original equation and replace every input, every x, with negative 10, we would run into a problem not just in one argument, but in two arguments. Now, even if the second argument instead of x plus 9 was, let's say, x plus 11, which in that case, negative 10 plus 11 is 1, which is still greater than 0. Even if that were the case, if it fails as an input possibility for even one argument, it fails for the entire equation, right? So we know that negative 10 is not going to work because negative 10 itself is not greater than 0, and certainly negative 10 plus 9, which is negative 1, is also not greater than 0. So the only solution here would be the solution set containing the number 1. So that's the only place, the one and only place, where this graph crosses the line y equals 1. Okay, let's see if you can apply these two examples now of what's going to happen when we solve logarithmic equations after condensing to one more example. It says, could you solve in example 3 the logarithmic equation ln? What did that mean again? The natural log, good job. And that meant we had base e, Euler's number, right? So we're going to write that in anytime we see an ln, okay? So we're asked to find out, when would this graph equal this graph? Again, Desmos or a graphing utility could check that, but we're going to do it algebraically without a graphing utility right now. So what we want to do is we want to see which of these two situations from the previous slide applies. Do we have a logarithm equals a logarithm with the same base on both sides, in which case we set the arguments equal? Or do we have a logarithm equals a number, in which case we switch back to exponential? Okay. Well, this is the first case, isn't it? We do, in fact, have the same base. A logarithm equals a logarithm with the same base. So we set the arguments equal in this situation. So it didn't matter what the base was. That throws some students for a loop. What happens to e? Nothing, because it didn't matter what the base was. If two logarithms of any base are equal to each other and they're the same base on both sides, that must mean that the arguments are equal. So I will simply set my arguments equal. The square root of 2x minus 1 must equal 2. At this point, we're back to a lower level algebra problem again, where we're going to have to remember how to solve an equation involving a square root, and then check if our answers are actually valid inputs. So let's take a look. Well, yes, we can remember that to take a square root and get rid of it, we have to raise both sides to the second power. Again, feel free to pause and do it yourself and check your work. Okay, now once you've squared a square root, that lifted the radical. So you just had 2x minus 1 is equal to 2 squared, or 4. Adding 1 to both sides, you'd get 2x is equal to 5. It's a nice linear equation. So x must equal 5 divided by 2, also known as 2.5. Okay, so before you declare with confidence that you have your answer, check if it actually is a valid input in each argument. The second argument, there's nowhere to place it because it's just a constant 2. But in the first argument, if you replaced x with 5 over 2 and then multiplied by 2, the coefficient, the 2's would cancel, leaving you with 5 minus 1, which is just 4 under the square root, which is 2. So this is, in fact, going to give you an argument which is greater than 0. And if that is happening, we've satisfied our restrictions for possible inputs of logarithms. So our answer would simply be the solution set with 5 over 2, or 2.5. So that's the one and only place where that logarithmic graph is crossing the other. And you could verify that with technology, a graphing utility. Okay, so we've practiced a couple of logarithmic equations at this point. But there's one other skill that I'd like to look at. So let's take a look at how we can put all of this together and kick this up a notch, something you probably haven't done before. Let's take a look. In example 4, we're going to do something, we're going to attempt to do something that has never been done probably by you when talking about logarithms. What I mean by that is, we've done this with lines, we've done this with parabolas in the past, where we give you 2 points and we say, hey, could you tell me the equation that goes through these 2 points in a linear manner or in a parabolic manner? So for example, I'm giving you 2 points here. When x is 1 and y is 1, so 1, 1. Point. When x is 5, y is 7. 2, 3, 4, 5. So there's 5. 1, 2, 3, 4, 5, 6, 7. Somewhere up yonder. Okay, so we have these 2 points, 5, 7, and 1, 1. And what we like to do is find an equation that goes through the 2 points. Again, if this was a line, if this was a linear model, if that's what they were after, a linear model, hopefully you would know exactly what equation to use. Can you think of one? Yeah. Y equals mx plus b, our slope-intercept form. If this was a quadratic model, meaning a parabola, so this is linear, parabola looks something like this, right? If it was a quadratic model, which looks like a parabola, you might use something like y equals ax squared plus bx plus c. That's the general version or the standard form. You can go back and check on those if you've forgotten what those look like. But right now, what we're going to try to do is try to find an equation of something that goes through these 2 points, but it's not a line and it's not a parabola. They would like it to be a logarithmic function. So they tell us what type of model it is. Now, right now, we're just making one up. We're saying logarithmic. I could have said exponential or linear or quadratic, right? In real life, this would be under a category called regression analysis, and you would want more than 2 points. You'd get 3, 4, 100 points, and you would ask your technology to find the type of equation that best models the situation. Is it truly linear? Is it truly quadratic? Is it truly exponential? Is it truly logarithmic? Because different data is modeled by different functions. And you would use something called a correlation coefficient, R, and the closer that R is to 1, that's like 100% accurate, meaning it goes through all the points perfectly, the better. Okay, but in this case, we're just handing you 2 points, and we're kind of boringly saying, could you find a logarithmic function that goes through them, just for practice, okay? Well, here's what I remember. Logarithmic graphs are either going to grow or decay, and in this case, it looks like it's growing, but they look something like this, didn't they? So I remember that that's what logarithmic growth looks like. And they've suggested a type of model for me to use. They would like me to use this logarithmic model. So at this point, we're not expecting you to memorize it, but this is what they're giving you. Y should equal some constant letter c plus some other constant letter b times a logarithm. In this case, we'll start off with base 10, a common log, whose argument is x. So starting at this place, could we find an equation that goes through both points? Well, of course. If you're wondering how this would work graphically, this part is our normal logarithm part, which is telling us that it's growing in a certain type of way, so like the one up here I've graphed. The b in front of it, remember what that does? If you put a number in front, it stretches it, so it's stretching it potentially, whatever b is. If b is 2, your y values are twice as big. If b is 1/2, we've shrunk the graph, we've compressed it by a factor of 1/2. And finally, the number c, the constant, you might be more comfortable if I put c at the end of the equation, right, plus c. That would move the graph up or down c units, okay? So this gives us the freedom to actually move our graph to physically sit on top of both points. That's the goal. So our job, just like if we were finding a model that was linear or quadratic, we'd have to solve for each of those constants, in this case for b and c. So let's use our first point to build our system of equations here. So for our system here, I'm going to use the point 1, 1 and see what that gives me. Well, that would mean at an input of 1, my output should also be 1. So when x is 1, y should be 1. So that would mean my output y should be 1, following the model. I don't know c, and I don't know b, so I just write them. Times a logarithm, implied base 10, but this time my input is supposed to be, x is supposed to be 1. Good job. Now, normally, you're going to have a nasty situation, okay? But in this case, we built it very nicely for you by giving you an input of 1 there. I'll show you in a second how this is very helpful. But let's get our second point going. Our second point is 5, 7, meaning when the input is 5, the output is 7. So the y value should be 7 when the input is x is 5. So I copy my c and my b times log, but this time my input is not 1, but 5. So what we have here is a system of equations. And in our next video set, when we get to our next chapter, we'll be talking more about ways to solve these systems of equations, involving something called matrices. But for now, we'll just remember that we could have used substitution or elimination at the very least to solve a system of equations that has 2 variables in it. But this case, I promised, was going to be really nice. And here's why. Anytime we have a logarithm, it doesn't matter what the base is. If the argument is 1, remember what that meant? If we had a log, any base whose argument was 1. Well, this means that the base to that power must give me 1. Well, what must the power be? That's right, 0. So that's another logarithmic property that if you don't remember, you should review from that link I sent at the very beginning of the notes. So in this case, if we know that because the argument is 1, that entire logarithm is just 0, well, this is going to turn out to be easier than we thought. Because b times 0 is 0, I would just get that this whole thing then becomes 0. meaning I have c equals what? 1? Okay, so now that I have c equaling 1, I found that c is equal to 1. My model just got a whole lot nicer, right? Now I could go back down here and replace my c with 1. So let's just go ahead and erase my c and put in what we know it is. It is 1. All right, so now I have 1, and it's supposed to be a plus my base times log 5. Okay, well, how would I solve that? Well, I'm really solving for b, aren't I? And b is next to a number. Log base 10 of 5 is just a number. So I could solve this just like I was solving any linear equation by isolating b. So I begin by subtracting the 1 from the 7, and I get 7 minus 1 is 6. So 6 would equal just positive b times the logarithm whose base is 10 and whose argument is 5. So log base 10 of 5. Finally, I could get b by itself by undoing multiplication on both sides using division. So dividing both sides by whatever is touching b, since I'm isolating b, I would get that b must equal, you see it? Yep, it's 6 over log base 10 of 5. So now I have my b as well. So if I wanted to write down the equation, one way I could write it, a little clunky, but let's write it out, would be that y should equal my c value, which was 1. So it's been shifted up 1. We can kind of see that from the graph that I had sketched above. Plus b, we're going to insert our b now. Here we go. b is 6 over log base 10 of 5, right? Times, it's supposed to be next to log base 10 of x, right? So at the very least, if you gave a professor this answer, your professor should be proud of you, right? You found the two constants, you have a model, you could put this in any graphing utility, Desmos or a calculator, and it would show the graph that does in fact go through those points. And more powerfully, you could then use the graph and this equation to find any location on the trajectory. But if you were looking at the back of a textbook, and when you get into higher level math classes, you're not usually going to have access to lots of instant feedback. Instead, you'll look at the back of a textbook and you'll see an answer that doesn't look anything like yours. And your job will be to realize whether or not your answer is saying the same thing in a different way. And sure enough, our answer could be written in a much cleaner way. Why? Because we had something called the change of base property, which said if you have a logarithm whose base, let's say, is b, and whose argument, let's say, is a, we could write that as a common log, so base 10, of the argument a, divided by the common log argument, base 10 again, of argument b. So the log of the argument over the log of the base. It could also be the ln, the natural log, of the argument over the natural log of the base. Either one of those is fine. Now in this situation, I would recommend, if we're trying to get our equation to look like they've asked us for, which is base 10, I would recommend using the common logs, base 10. So if I did that, I would say right here that log of x over log of 5 is really what? Well, let's take a look. This would be y equals 1 plus 6 times log, in this case, it would be base 5 of x. Okay, so if I wanted to actually condense it into a single logarithm there, that would be an easier way to write this. Or I could write it as 6 times log base 5 of x plus 1. In other words, it was a logarithm whose base was 5. It's been stretched by a factor of 6 vertically, so the y values got multiplied by 6, and then shifted up 1. And that does make more sense if I look back at my picture. All right, so these ones can take a lot of time. The setup is lengthy, it's tedious, and if you make one little mistake, you're going to be off. But the way you know you're right is you could actually check those points, right? You could plug in the inputs and see if you get the right outputs. So that's always something to do once you get your model. Does this actually model my reality? Okay. All right, so if this wasn't as nice, if we didn't give you an argument here whose base was 1, you would have used substitution or elimination. Usually elimination, you'd subtract both equations and see what cancels. In this case, probably the c's would cancel, and then you'd use your properties to solve for b. Okay, so those will take time and practice, like everything else we've been doing so far this semester. Well, that's it for this video. At this point, it's up to you. Remember, math is not a spectator sport, so go practice. See you next time.